That's just, oh my. Hello? Hi? Is this too loud? Is this, spectacular. Great. Well, holy cow. Is this worlds away from 2015 Edinburgh? Was it 2015, Donald? 2016? 2014. 2014. Wow. 2016 says Andres. Well, good, 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 good. So, but man, is it amazing? Is it amazing to be here in Taipei and to see so many familiar faces and see so many new faces, and yeah, I'm spectacually grateful for the organizers for organizing this and for giving me the opportunity to talk about some things that I'm really excited about. So I ended up, I ended up. Can I get a show of hands for people who identify as cosmologists in the room? Okay, lower your hands. Can I see a show of hands for people who identify as amplitudes people in the room? Okay, of the people who identify as amplitudes people, keep your hand raised if you identify as sort of positive geometry, surfaceology. Okay, some not so many, but I did include a special bid just for you guys. What about people? Can I have a show of hands for people who've calculated tree level gravity predictions using double copy? Okay, good. What about multi-loop level? Okay, good. So cool. So this talk I did kind of rewrite when I realized that I might be one of the first people speaking in any depth about double copy, and so here, without further ado, so what am I talking about when I say the roots of inflation? I mean, can I come up with gauge theories that double copy to give me the predictions of the effective field theory of inflation coupled to gravity? So that's what I'm talking about. That's what I mean by the roots. So I mean the roots in a sort of square root sense and a double copy square root sense. Good. Maybe. Okay. So to motivate, because I'm going to be introducing some building blocks that aren't necessarily super familiar even to amplitudes people who use double copy to calculate multi-loop gravitational predictions. I'm going to motivate by kind of zooming in on what I'm thinking about as what's useful in double copy. Then I'll take us through a brief introduction to the effective field theory of inflation, some of the ingredients that go on, how we go beyond Lorentz invariance, how we go beyond adjoint FABC structure constants and creating a double copy that yields the same predictions as the effective field theory of inflation. And then I'll close just briefly talking about some future challenges and opportunities. Great. So what makes a useful double copy? So there are all sorts of ways of taking predictions and just smushing them together, right? Take products of predictions. What do we want for something useful? We want something that takes things that were gauge invariant, and you combine them and you get something that's diffeomorphism invariant. Right, and then you can use that same structure all over the place to couple to things in predictions that are gauge invariant ways that give you predictions that are diffeomorphism invariants. And we'd like to do this in a way that preserves unitarity, locality, causality, that preserves everything we care about in terms of our predictions, although we can use building blocks that don't necessarily preserve all of these things, right? So we can double copy to conformal supergravity theories, for example, right? But we're doing it in a framework that we trust. We trust in this procedure. I put this here just to point out that, and these are just double copies in the sense that we're familiar with for many, many years now, many years. So in terms of like sort of adjoint type FABC satisfying antisymmetry in Jacobi, you get all sorts of theories that you can pry apart in terms of a small number of building blocks that you combine together in different ways to get various theories. Okay, but I want to zoom in on gauge invariant. And the point that is intimately familiar, especially to all the amplitudes people, but I think hopefully familiar to all of us, is the fact that individual Feynman diagrams don't mean anything, right? So an individual cubic graph for Yang-Mills, just 5 gluons interacting, is not gauge invariant. It doesn't mean, it depends on how we tell the story. It's not a physical prediction, right? And to be real specific about it, when I dress, this topology with its color factor, its kinematic numerator containing polarizations, momentum upstairs, and divide out by the propagator structure, and I take one of my polarizations of momentum, I don't get 0. It's not gauge invariant, right? But in Lorentz gauge, you just choose your generic gauge. Now, of course, I didn't include contacts, right? So I can include the contacts. We know we need contacts at 4 point. We need the contact diagrams at 4 point. That's the whole point of the contact diagram at 4 point, is to give us gauge invariance, right? We can derive it by starting with the 3-point amplitude, squishing them together and say, oh, what do we need to add to our 4-point amplitude to get gauge invariance? You need the 4-point contact. But even just adding the 4-point contact in is not enough for gauge invariance. In fact, how do we get something that's gauge invariant? Well, we get things that combine all sorts of different properties. So at 5 points, we need to combine all 5 of these different topologies, and then we've built something. Then we've constructed something that's actually gauge invariant. So the color weight of just this guy multiplied by the kinematics of all of these guys summed together, this vanishes. This is gauge invariant, right? So this is these things, right? This is what people call color ordered amplitudes, or partially stripped amplitudes, or Sashstev polytopes at higher and higher multiplicity. And the reason they all speak together is because of properties of the Lie algebra structure constants. The things that are intimately part of our predictions in Yang-Mills is the fact that we dress things with color weights. And these color weights aren't independent, right? They satisfy antisymmetry in Jacobi. And that lets us reduce to a basis of color weights that's much smaller than the number of graphs we write down for any given prediction, right? So the fact that the color factors have relations allow numerator gauge dependence to cancel in, for example, all 15 distinct cubic graphs you'd write down for 5 points. So if you dress each of these guys with its kinematic weight and its color weight and its propagator structure, you add them all together, you've got something gauge invariant. It's because these color weights speak to each other. Just to be real pedantic about it, the fact that we have antisymmetry in FABCs is why we only have to write down 15 graphs. Bananas, getting used to this. All right, 15 graphs. I only have to write down 15 graphs instead of various other permutations, right? I don't have to write down this guy, right? Because it's just a vertex flip. This guy, incurring a minus sign in the color factor. Now, of course, incur a minus sign in the kinematic weight as well. Otherwise, I wouldn't have Bose invariance. In fact, well, I could have some symmetry, but it'll get wiped out. If I sum over something symmetric with something antisymmetric, of course, it gets wiped out. Color Jacobi means the Jacobi identities I wrote down just a slide or two ago. Means that there are 6 basis graphs at 5 points. So instead of all 15 of these guys, right, I only need these 6 basis graphs. You'll see I'm holding like the bottom 2 guys fixed. I'm permuting over the top guys, and that gives me all the independent color weights I need, and that's what let these guys, decomposing them into their basis, they all had a contribution that was speaking to this guy. So when I took all the graphs in my permutohedron, all the graphs in my full amplitude, and I express things in terms of the color weights, and I express the color weights in terms of a basis, right? These 5 guys, corresponding to the dodecahedra, add up, contributing with this color weight. And this thing's gauge invariant. All right, so again, just to reiterate, the fact that color factors have relations allows numerator gauge dependence to cancel. And so this is where sort of this idea of building a useful double copy comes in. That my numerators didn't need color factors, they just need something else that obeys the same relation. And then their half of diffeomorphism invariance is preserved. And if it happens for both sides, then I've promoted gauge invariance to diffeomorphism invariance. And because gravitation polarizations factorize, this duality between color and kinematics allows for a meaningful double copy. I want to give just right here, while I'm on this, before I talk about generalizations to other types of color factors that will want to be color dual too. I just want to briefly say a few words for our positivity friends, which is along the lines of how you can take generic multi-loop amplitudes and in generic representations, but if you have control over the planar sector, you can push that non-trivially to the non-planar sector without ever having to sew trees together, just by using properties of what the loop integrands have to be on shell. And so this gets down to how many of these associahedra you need in order to touch a full amplitude. You might think that you'd need m-2 factorial of them, because that's what's required to touch every graph at least once. For example, here's one guy, it's another guy, it's another guy, another guy, and a final guy. And so with those, I've touched every graph at least once. But because we have this sort of duality between color and kinematics, we actually only need to talk about this boundary data, right? And then Jacobi relations push everything in. So every triangle is an occasion for Jacobi to be satisfied. And just by specifying the boundary, this permutahedra, the 6 I talked about were a basis for color weights. If the kinematics obey the same relations, those same 6 form a basis. And if I just specify those guys, then I have Jacobi relations pushing data in. And I only need m-3 factorial of these ordered amplitudes of these Stashev polytopes, these associahedra, to touch all the boundary guys. So at 5 points, I only need 2. And we can use this at loop level. But just to write that in terms of equations, any ordered amplitude, right, I can write to a basis of n-3 factorial ordered amplitudes. Okay, where these coefficients here, these coefficients here are just rational functions of kinematic metal stamp variables. Okay, and all of what I said about trees applies to graph organized integrands under on-shell conditions. We've got various cut topologies that we can use to build up our integrand. We've got various ordered cuts we can perform that touch different graphs for this same topology, right? So if I'm talking about this guy in terms of ordered amplitudes, right, there are under Kleist-Coif, there are n minus 2 factorial distinct ones of these, are under under the PCJ relations. There's n minus 3 factorial associated with each of these cuts. And the idea is that, that if I have some basis cut orders, if I know the basis cuts that contribute, because of some seeded data, the others follow by pushing out field theory relations, by tiling them out. And what's a distinct sector of integrands for gauge theory is planarity is incredibly distinct, and something that that our positivity friends really enjoy. And my point is that we can identify planar dominated cut topologies if the basis cuts only contain planar graphs, and we can identify when planar dominated cut topologies span everything that's needed to construct the full multi-loop amplitude. So for example, at 3 loops in n equals 4, we've only got 2 planar graphs contributing, but with the data from those 2 planar graphs, you can just recycle the information on shell conditions. I'm not talking about like sewing trees together, but just applying field theory relations to cut data here so each of these cuts is planar dominated, is completely specified by the information encoded here, and then by choosing different cut orders, you can tile that data out to non-planar topologies in a way that's completely ansatz free. You're just pushing it out under cut conditions until you've saturated all on-shell conditions. And so this is one path to gravity from positivity, which is to constrain your planar sector, use cut tiling to get to the non-planar sector, and then generalize double copy, which takes any given representation you have and just pushes it through to gravity. This is an occasion to advertise what I believe we'll be hearing from Zvi on Friday, which is some very efficient ways of doing generalized double copy. Okay, back to the main thrust of what I'm talking about. Our adjoint FABC, anti-symmetry and Jacobi rules the only way to striate gravity predictions in terms of double copies. And this is posed like this. It's I don't know, right? It seems kind of open, but we have examples. We have examples now that are kind of venerable, over a decade old. One of my favorites was by Song and Tristan, Phil and friends, where they showed that n equals, in 3 dimensions specifically, n equals 16 supergravity has 2 very different striations, right? One double copy in terms of our familiar adjoint type double copy relying on Jacobi identities between n equals 8 super Yang mills and n equals 8 super Yang mills in 3 dimensions. But then something that was much less familiar to me, even though it was all the excitement just a few years earlier. I remember a lot of excitement in late 2010s about DLG theories. These guys don't obey a Lie algebra. They obey a 3 algebra, right, with associated multigraph relations like this. But if you organize the kinematic information in a way to match that striation, that 3 algebra striation, then you can throw out the color weights, replace with kinematic weights, and land on exactly the same supergravity theory that you got from double copying n equals 8 super Yang mills the familiar way in 3 dimensions. Okay, so this is one example, but and it's a spectacular example, and it's super rich, and it's very fun to play around with. But there's a way of asking this question, I think, that I think makes it a little more obvious that there are all sorts of ways to pull things apart, right? So instead of just asking about gravity, right, just talk about permutation and variance in general, right, is breaking things apart in cubic graphs in terms of things that obey antisymmetry and Jacobi the only way to span a space of permutation invariance? And it's clearly not, right? So with this in mind, right, it behooves us to spend a little bit of time thinking about all sorts of different building blocks we can use to make tinker toys that let us pry apart permutation invariance in a way that lifts permutation invariance to gauge invariance, right? And a wonderful playground for doing all of this in a way that's both accessible and useful is to start playing around with constructing and classifying effective field theory operators. And the nice thing is while you can start by throwing ansatz at higher and higher mass dimension under these algebraic relations to see, ooh, what can I do to satisfy taking graphs that have this permutation symmetry and satisfy Jacobi like this. You soon realize when you're playing around with this that these building blocks, they speak to each other. There's a way of combining tinker toys to build more tinker toys that look exactly like what you started with. So if you have, for example, like a minimally coupled scalar, right? Something that starts off with kinematic weights that are a single Mandelstam in mass dimension, and you have a way of combining kinematic weights to construct things that satisfy your algebra, a way of composing things together. So I've got things that satisfy Jacobian antisymmetry, things that satisfy Jacobian antisymmetry. Can I bring them together to build a new thing that satisfies Jacobian antisymmetry? And it turns out you absolutely can, right? So there are composition rules for all sorts of algebras, all sorts of ways of assigning relationships between graphs and permutations around them, and a laddering operation that lets you climb to all mass dimension. And it turns out that at the end of the day, a lot of this is just figuring out how to sprinkle derivatives, and what does that mean? Just how to sprinkle scalar invariance. And that's a simple problem, right? And that's something that's absolutely solvable in terms of a very small number of building blocks. And so good. So this is to set the stage for talking about. I started a little late. This is all to set the stage for talking about the effective field theory of inflation. And so this is a venerable effective field theory in cosmology that's only gotten more and more excitement as time went on. The idea is everybody has their favorite models of inflation, but really how different are they? And when we're looking at the data, can we hash it to some Wilson functions, some Wilson coefficients in front of operators, so that we can see how special our theories are? All right, so this is the idea for this is just something. It's something very general. And now I'm talking about a particular effective field of single field models. There are all sorts of effective field theories of inflation involving fancier and fancier things. But I'm just talking about this old sort of simple idea. And so the idea is you can write down the most and I should give credit to Xiaoshen. So Xiaoshen, after or around the time he and Dan Green and a collaborator wrote this super fun paper looking at soft theorems in the effective field theory of inflation, which is the first time I'd ever actually seen somebody playing around with amplitudes in this theory. Right? He wrote up some notes for me because, or I don't know, he wrote up some notes and he shared them with me because I wanted to sink my teeth into what was going on. So anyway, so I just stole this from Xiaoshen. So you can write down the most general boost breaking Lagrangian. See there? I've got time derivatives. I'm breaking boosts. Got a speed of sound, right? So I've got some difference in what I'm doing with time and space. The idea is that the boost is spontaneously broken, so you stuck a word, and you jump up and down. You just see that Wilson coefficients have to be related. But the point I'd like to zoom in on is the first interesting amplitude, which is going to be right here. So what's a three-point amplitude in the theory? It's just the product of energies, all three lines. We learned two important lessons from just staring at this guy. One is a cool thing, which is something we're not used to for Lorentz invariant theories, which is you can have a non-trivial three-point amplitude with just scalars, right? That's cool, right? Because our Mandelstams, or Lorentz invariants, vanish at 3 points. Our kinematics vanish. Our kinematics vanish at 3 points, which normally means that our three scalar amplitudes tend to be kind of boring, right, for scattering amplitudes. But once we allow energy, we can do something non-trivial with it. Another thing we notice right away is that the double copy of roots, if we're going to pry this apart, it needs a DABC structure. It needs a symmetric structure. I can't construct this out of Bose symmetric things that satisfy anti-symmetry. It does. Are you playing The Office? Is this some sort of? Okay, I'll use it. Dude. Okay. Great. Cool. Double copy roots need DABCs, right? And so you can imagine, kind of trivially, one way of building this amplitude is a double copy with DABCs. I just have one copy take all the energies, and then I've got some sort of scalar phi cubed on the other copy. It's not super exciting, but it was only 3 point. Let's see where we go from there. We go from there is looking at 4 point, and it advanced on the computer and did not advance on the screen. Does somebody want to? Oh, okay. Oh, now, okay, good. There was a non-trivial delay, right? I wasn't imagining it. Yeah. Okay. Good. So, but this is spectacular. This 4-point amplitude is spectacular. Every person who's familiar with double copy, I think, is seeing the same thing, which is looking at this, right? And this guy's a familiar double copy at 4 point. It's a double copy between nonlinear sigma model pions and a minimally coupled scalar. Okay, that's cool. This type of minimally coupled scalar, maybe you'd see in like a Born-Infeld multiplet or whatever, but just a minimally coupled scalar, covariantized free scalar. That's awesome, right? You combine that with the fact that looking at the energies on the poles for how it had to factorize, you see exactly the type of energy to the 6th power. You get my summary together. Single copy theory we wrote down at 3 points, right? So this suggests that our root of inflation can be described by nonlinear sigma model pions plus additional boost breaking energy dependent terms that come in with DABCs, and these guys are sitting around and they can own the effective field theory of inflation Wilson coefficients, and you're just double copying this with a beautiful theory of minimally coupled scalars with the addition of a scalar DABC phi cubed term, right? And it's relatively straightforward, although it takes a little bit more work as you go higher and higher multiplicity, because the top energy showing up starts growing rather largely, right? So you've got like make it 3 at 3 points, make it 6 at 6 points, so make it 9 at 9 points. And these are all the different ways you can combine the energies to satisfy your color and kinematics. But at the current time, we have consistent color dual pions and boost breaking terms through 5 points, and a covariantized 3 scalar plus phi cubed just works in a color dual way, almost from Feynman rules, as high in multiplicity as you'd like. As I mentioned, the energy growth is non-trivial with multiplicity, so functional Ansasse can get quite large. Thankfully, there are soft theory limits for the effective field. There's soft theorems for the effective field theory of inflation, which is an exciting opportunity for soft theorems to beat bootstrapping these guys via Ansasse, at least for helping constrain the types of things you write down. You can ask, can we couple to gravity? And of course, the answer is yes. All you need to do is add Yang-Mills to your pion terms. You already had Yang-Mills speaking to your minimally coupled scalars, so now you just need to add Yang-Mills to your pions. But we already know how to do this, that gauged pions are the building blocks for alpha tractor models of inflation, right? So this is something that's we've already explored. Good. So I am, if I understand correctly, out of time. So I'm going to summarize that if there's a take-home message, I want you to trust double copies that consistently list gauge invariance to Diffie. And I think that's what you want to sink your teeth into as you're playing around with how you can pry apart predictions of all sorts, using effective field theories to learn more about what building blocks are around, how they can play together, is super fruitful. The effective field theory of inflation is incredibly fun. And so what's the planned strategy? I mean, the warm-up here is on amplitudes. We want to lift to wave functions and correlation functions. There's so much to do here in so many different ways. Absolutely feel free to jump on board. And I look forward to speaking with all of you over this next week.
All right, thanks for that entertaining talk. So is there any questions for John Joseph?
JJ. You suggestively used this notation DABC to probably suggest a correspondence between the symmetric tensors that appear in Lie algebras, particularly the SUN series. Where does that come from? I mean, why not just? There's a lot more symmetric rank 3 tensors than there are those associated with SUN.
Yeah. And so great. So, for example, for the games I'm playing here, just symmetric rank 3 tensors, but any symmetric rank 3 that you combine, like a D with an F, you'll still get a Jacobi. And so you rely on that. You count on that. That's part of the constraints of what you're building. But I'm not playing any constraints that we normally associate with SUN further down into like double trace terms or yeah.
The same structures, the same input that gives you that leading order EFT for the Goldstone also gives constrains the higher order derivatives.
Yes.
Can you see how those are also constrained from the same input in the double copy, or there has to be new structure added upon it?
Great. And so I haven't looked at higher derivative terms, right, in the effective field theory of inflation, but a large part of the game over, I'd say, the past decade has been getting more and more comfortable with various ways of UV completing in a color dual consistent way all sorts of scalar theories, right? And I think starting from what you get from string theory disk integrals as a doubly color ordered theory, so maybe you've heard of Z theory integrals, or so you can take the open superstring and pry off Yang-Mills and replace it with color weights, and you've got higher derivative corrections all the way to the UV, right? Completely determined by these disk integrals.
in a way that's consistent around certain symmetries with completing pions or pions plus biadjoint scalars. All that to say is we've got tools that looking at higher derivative corrections that are very much along these lines, but I haven't looked at it yet. I've been just staying with these leading orders so far.
Great. We're really out of time, so let's thank Jonas again.
Oh, yeah, we have gotta have coffee now. We have changed the setup slightly to create more space. So it's gonna be coffee at the same place as it was before, but the snacks and kind of around the corner. So you will see them. Okay.
Okay.